Hi everyone, welcome back to sisyaclass YouTube channel. So today we are going to discuss D and F block elements and coordination compounds. Two chapters we will cover. I hope you have seen the last session in which we have covered P block elements. I hope you have solved questions based on that. A lot of facts were involved, so I hope you have revised it. Okay. So in today's session we will talk about D and F block elements, its properties, and magnetic movement, some of the questions related to it, and finally we will talk about coordination compounds, the different theories involved. Okay, so I hope we are following the EAPCET series. Today we are going to cover these two chapters. Then in the next session we will talk about organic chemistry, haloalkanes and haloarenes. So try to revise that also for the next part. Okay, so before we begin, let me introduce myself. Then we are going to start with our topics for today. We will understand some of the important points. Then we will solve questions based on it. Okay. So my name is Nidhi. All those who are following the channel, we always take the class at 3:30 p.m. So I hope we are following the series. I hope we are solving questions from your side. My name is Nidhi. I have secured AIR 32 in CSIR NET examination. I have 6+ years of experience. I teach these competitive examination, NEET, JEE, and today we are going to talk about the EAPCET series. Okay, so stay tuned. Try to keep up with the question. Try to solve it yourselves. There are no numericals involved in today's session. Okay, there are some calculations involved for sure for calculating the magnetic moment, but they are so easy. You will understand it very quickly. So try to follow these steps I am telling you, and then you can solve the questions quickly. You don't have to show the entire thing that I am solving it by substituting these values here and there. No, you have to solve it quickly. You have limited amount of time there. In D and F block elements, it is mostly theoretical. For coordination compounds, you may have some calculations involved. We will see those questions also. Okay, so let's see what are the topics we will cover today, everyone. So we will talk about D and F block elements. Okay, then in coordination compounds we will discuss coordination number. What do you mean by magnetic moment? How do we calculate it? How the magnetic moment varies if you have a strong field ligand, if you have a weak field ligand. What do we mean by spectrochemical series? How do we arrange the different species in spectrochemical series? That means you should know the difference between a weak field and a strong field ligand. That is very, very important. You have to cram the spectrochemical series. You will see a lot of questions today in which directly they have asked you the order of the strength of the ligands involved. So if you know the spectrochemical series, you can mark the answer in a few seconds, provided you know the series. So please try to remember spectrochemical series. Extremely important. Direct questions. What else we are going to use the where else we are going to use the spectrochemical series? We are going to use the spectrochemical series to compare the strength of the ligands, and that will help us to determine the magnetic moment of certain complexes. That will help us to determine the hybridization of certain complexes, whether it is an inner orbital, outer orbital complex. You can decide that also on the basis of the strength of the ligand. So that makes your spectrochemical series extremely important. Please try to remember it. Okay, so once we are done with that, we are going to discuss different theories by which we can explain the bonding in our coordination compounds. So we have valence bond theory, we have crystal field theory. We will understand certain important points of both of these theories, and then we will solve questions based on them. Okay, so let's begin with our content part first. So first of all, D block elements. So you have learnt about P block elements, group 13 to 18, right? We have covered that part. We have learnt about a lot of facts about P block elements, right? Now let's talk about D and F block elements also. Okay, so your D block elements, they are found in groups 3 to 12. So group 1 and 2 will be your S block, as you all know. Then from group 3 to 12, you have D block. And finally, group 13 to 18, P block. This we have already covered. This we are going to cover after a few sessions, and today we are going to talk about D and F block elements. Okay, so this is found in group 3 to 12 of the periodic table. They have partially filled d orbitals in their ground state or their most common oxidation state. You will find one such question in which they will ask you which of the following are known as transition elements. So don't think that everything that belongs to D block is your transition element. No. In order to call a certain compound, in order to call a certain element as a transition element, it must have partially filled d orbital in its ground state or its most common oxidation state. If the d orbital is completely filled, if your d orbital is completely empty, you will not call it as a transition element. Then it will become a non-transition element. We will solve one such question today. So please try to remember this information. Okay. See the next part. It shows variable oxidation state. Why? Because the N-1D and Ns electrons are involved in bond formation. See, generally what do we see? If you talk about s block elements, your last electron enters the s orbital. So those electrons are taking part in bond formation. In p block element, your last electron enters the p orbital. So those electrons are involved in bond formation, your valence shell. But in case of d block elements, your electrons in ns orbital and n-1d orbital, both orbitals are involved in bond formation. That makes it different from your s and p block elements. This is what we are trying to say here, that both n-1d and ns electrons are involved in bond formation. That is why it shows a variety of oxidation states. Okay. A lot of oxidation states are shown by one single element. That is a key property of D block elements. And they can ask you the reason for it as well. You know the reason now. Okay. See the next one. It exhibits color. In order to exhibit color, it must have unpaired electrons. How are we going to understand that it has unpaired electrons? For that, you should know the atomic number. You should know how to fill the electrons in the orbitals, and then you will decide whether you have unpaired electrons or not. And if you have unpaired electrons, your compound will show color. What else? It will be paramagnetic. Okay. So it will exhibit color, it will be paramagnetic, and it will form a lot of complexes also. And it also shows catalytic activity. So you must have learnt about a lot of reactions in which the catalysts are from D block. Do we remember the question we have covered in which we have seen the production of ammonia from Haber's process? We have talked about what is the catalyst there, what is the promoter, what is the poison. So the catalyst was Fe. Fe belongs to D block. Like that, you have plenty of other examples in which the catalyst belong to D block. Okay. So that is a key property of D block elements, that they exhibit color, not all of them, but if they have unpaired electrons for sure, they are paramagnetic. Again, if they have unpaired electron, then only you can call them as paramagnetic. If they have completely paired up electrons, they will become diamagnetic. They will not show color in that case. Okay. Then they are going to show catalytic activity. Alright. And alloy formation is also possible with your D block elements. We have covered questions based on alloy formation also in metallurgy. If you all remember, extraction of metals and metallurgy, we have covered questions based on that as well. Alright. So these are some of the examples of the metals which belong to 3D series. Okay, we have 3 series here in D block, 3D, 4D and 5D that we are concerned with. All these elements belong to your 3D series. Okay, so we have iron, copper, zinc, nickel, chromium, manganese. Alright, let's see some more properties. So what about F block elements? Your D block elements are called as transition elements. In order to call an element as transition element, it must have unpaired electrons in its d orbital or in its most common oxidation state. In order to call an element as an inner transition element, your last electron must enter f orbital. Okay. So we have lanthanides and actinides in case of F block. 4F series is known as lanthanides and 5F series we call as actinides. Okay. These also show variable oxidation state just like your D block elements, right? In D block elements also we have said that they will show variable oxidation state, a variety of oxidation state. In here also something similar we will see. Okay. Mostly +3 oxidation state is stable for lanthanides, while your actinides will show a variety of range of oxidation state. Do we have to remember these facts? Yes, they can be asked directly. Which of the following statements are true? Which of the following statements are incorrect according to you? That is how you can answer that question. Okay, and in that question you will see 3-4 statements. Okay, so you have to identify which one is correct, which one is wrong. Based on that, you will choose the correct option. Okay. Now they have highly reactive metals. They form colored ions. So we have seen your D block elements also show color if they have unpaired electrons in them. Same thing. F block elements can also show color provided they have unpaired electrons. If all the electrons are paired, your compound, your element will become diamagnetic, then it will not show color. Okay. Actinides are mostly radioactive, so you don't have to worry about radioactive elements. Not a lot of questions are asked from there. Okay, but you should know that your F block elements are divided into 2 series. We have actinides and we have lanthanides. Okay. Now, some important terminology that you must know about for your coordination compounds. So you must have learnt about ligands, you must have learnt about coordination number, center metal atom. That terminology is important, very easy. You already know that. Let's revise it quickly. Okay. So what do we mean by ligands? Ligands are neutral or anionic species which donate your electron pairs. Your ligands can be positively charged also. Okay. So you can have positively charged ligands also. Only 2 you have to remember, not many. One is nitronium ion, another one is your anilinium ammonium ion, nothing else. Okay. So you can have neutral or anionic species which can donate electron pairs like ammonia, like cyanide, like chloride. Okay. But you can have positively charged ligands also. Not that much prominent, not a lot of questions are asked from there, but you should know about it. Okay. What else is there? Coordination number. What do you mean by coordination number? The number of ligand donor atoms which are attached to the metal is what we call as the coordination number. For example, this is a complex in which copper is your central metal atom, ammonia is your ligand, okay, and it is forming a complex. Now, how many ligand donor atoms can we see here? I have a monodentate ligand. We can classify the ligands into monodentate, bidentate, tridentate and so on. We are not going to go into detail. You already know those facts. So, ammonia is a monodentate ligand. There is only one donor atom which is going to bond with your central metal atom. Okay. So, I have 4 such ammonia ligands, 4 such monodentate ligands. What will be the coordination number of this complex I have written? It will be 4. Okay. So, this is what we are saying. The number of ligand donor atoms attached to the metal. Okay. What if we have a bidentate ligand? Ethylene diamine is given to us. Central metal atom, ethylene diamine. Now, this one is this is some charge I have written. I am just giving you a general formula. So, ethylene diamine is a bidentate ligand. So, don't say that the coordination number in this case will be 3. No, ethylene diamine is a bidentate ligand. 2 donor atoms are simultaneously bonding with your central metal atom. So, how many donor atoms we will see in 3 ethylene diamine molecule? 6, right? So, what will be the coordination number here? 6. So, don't just blindly count the number of ligands, that will not work. You have to count the number of donor atoms. For that, you must know what type of ligand we are talking about. Are we talking about a monodentate ligand, a bidentate ligand, a tridentate ligand and so on. Okay. So, this here has coordination number 6. Number of donor atoms you have to count. Don't count the number of ligands. Okay. Next, this was the first theory. Werner's theory was the first theory that tried to explain what type of bonding exists in your coordination compound. So, Werner's theory gave you 2 postulates: primary valency and your secondary valency. What is your primary valency in simpler terms? Just calculate the oxidation number of your central metal atom. That is known as primary valency of the coordination compound. What do we mean by secondary valency of a coordination compound? The secondary valency will be the coordination number of the complex that you have taken. Okay, so primary valency is oxidation state of the complex and secondary valency is the coordination number of the complex that we are talking about. Don't worry about anything else. So this is what we mean by Werner's theory. Okay, primary valency, oxidation state, secondary valency, coordination number. Okay, next, nomenclature. We are going to name the complex based on the ligands and the oxidation state of the metal. Again, you must have seen a lot of questions based on the nomenclature of your coordination compound. Very easy peasy questions. Focus on what type of ligand is present, anionic ligand, neutral ligand, positively charged ligand. Based on that, you have different terminology. So try to remember the table which is given in your NCERT. And in addition to that, you must know the oxidation state of central metal atom in order to write the correct name of the coordination compound. So oxidation number is equally important because you have to write it in the name itself. We will see some questions based on that as well. Okay, next, we have different types of isomerism, structural isomerism and stereoisomerism in coordination compound. So we will solve questions based on that also. Linkage isomerism, ionization isomerism, hydrate isomerism, we will cover that. Coordination isomerism, you have to identify what type of isomerism is shown by the compounds. We will solve one such question today. And if you talk about stereoisomerism, it can be further classified into geometrical isomerism and optical isomerism. Okay, geometrical for the cis and trans, and optical isomerism, if your compound is optically active, it will not have any POS or COS. If POS or COS is absent, then compound is optically active. If POS or COS, any one of them is present, your compound will become optically inactive. We will cover one such question today. Okay, last thing, different types of theories by which we can explain the bonding in coordination compounds. So as we have seen in the beginning also, we can explain it through valence bond theory. It will not tell you the exact detail about the bonding. Crystal field theory will help you there. Okay, but you should know the type of hybridization based on valence bond theory also. Sometimes it will give you the wrong answer, that would be its limitation. Then we go to crystal field theory. Okay, then what are the applications of your coordination compounds? They can ask you certain questions based on that also, that which of the following complex compound is used to treat cancer, cisplatin. They will ask you the structure of that compound, they will ask you the formula of that compound. So try to remember some important compounds and their applications. They may give you a preparation of an important compound and they will ask you what is the catalyst used there. So they can be related to your DNF block elements also or your coordination compounds also. Okay, so please try to revise the application part of your coordination compounds, not everything. There will be a small table that you will find in your NCERT. Try to read it, it can come directly. Okay, see the next one. Order of strength of the ligand. This is very, very important. You will solve multiple questions based on it. Okay, so what do we mean by spectrochemical series? In spectrochemical series, we will arrange the different ligands based on their strength. Okay, so you can have strong field ligands, you can have weak field ligands. Strong field ligands have the tendency to pair the electrons. On the other hand, your weak field ligands will keep the electrons unpaired. Based on that, your hybridization comes out to be different. And you have to identify the hybridization. You have to identify whether your compound is paramagnetic or diamagnetic. You want to identify what is the magnetic moment of the coordination compound. Spectrochemical series will help you there. So do we have to cram the spectrochemical series? Yes, you must. Okay, so we have arranged the different ligands based on their strength from weak field to strong field. Your weak field ligands will show smaller splitting. If you talk about the crystal field theory, in the presence of ligands, you have learned that your degenerate d orbitals, they split into T2G and EG in case of octahedral field. They split into T2 and E in case of tetrahedral field. Now the distance between the two set of orbitals that we have talked about, the splitting will depend upon the type of ligand you have taken. If you have a strong field ligand, the order of splitting will be higher. If you have a weak field ligand, the order of splitting will be lower. Okay, so this is what we have written here. Your weak field ligands will show small splitting and they will form high spin complexes. And your strong field ligands will show large splitting and they will form low spin complexes, and there is another name that we give them that can be asked to you. They will form inner orbital complexes. Inner orbital complexes. And your strong field ligands will form inner orbital complexes and your weak field ligands will form outer orbital complexes. So you should know the difference between them also. This also you will come to know if you know the strength of the ligands. For that you must remember spectrochemical series. Okay. So we have halogens in the beginning. There is a short trick by which you can remember the overall layout of the spectrochemical series. Obviously you have to remember the individual ligands, but for your understanding, we can have halogen donors, we can have oxygen donors, we can have nitrogen donors, and finally we will have carbon donors. Okay, like this. Halogen donors or halide donors. Let's write it as halide donors. Yes, halide donors. After that we will have oxygen donors, then nitrogen donors, and finally we will have carbon donors. Carbon donors will be your strong field ligands, nitrogen donors also. Oxygen donors and your halide donors, we consider them to be our weak field ligands. Okay. Oxygen, then nitrogen, and finally carbon donors. But you should remember the individual ligands also. Alright, that can be asked to you directly as well. Carbon donors. Alright, we will solve certain questions in which you have to arrange these ligands based on their strength. Okay. So the same thing we have written here, that your weak field ligands, they will cause small crystal field splitting, as I have already told you, and they will favor high spin complexes or outer orbital complexes. High spin complexes are also known as outer orbital complexes. And your strong field ligands will cause large crystal field splitting and they will favor low spin complexes or inner orbital complexes. So this was one limitation of your valence bond theory. Your valence bond theory cannot decide the strength of the ligands. Okay, valence bond theory does not know that this ligand is weak, this ligand is strong, this ligand is capable of pairing the electrons, this ligand is not able to pair the electrons. That kind of information is given by crystal field theory. Okay, so now we are done with the important concepts related to coordination, compounds and D and F lock elements. Now we are going to start with questions. So I hope everyone understood the content part, and I want everyone to solve the questions themselves and then see the answer, cross check whether you have given the correct answer or not. Okay, see the next one. the very first question. Identify the correct statements from the following. These are the kinds of questions that they will ask you from D and F block elements. Certain facts, certain important points about your D and F block elements in terms of statements. There will be no numericals involved here, so you have to remember a lot of facts. But those facts are so simple, those facts are repeated so many times that if you revise it once or twice, you will be able to remember it. Okay, so don't fear D and F block elements, it is a very easy chapter. Okay, read the question. Identify the correct statements from the following. Titanium in 4+ oxidation state is much more stable than titanium in 3+ or 2+ oxidation state. First of all, you must remember the 3D series of D block. Okay, in order to solve the question, you must remember the 3D series, you must know their atomic number, you must know their electronic configuration. Okay, then only you can solve this question. So please see the electronic configuration. If they talk about oxidation state, any question that they ask, whether it is stability of oxidation state or oxidizing power, reducing power, oxidizing nature, reducing nature, you can answer based on oxidation, you can answer based on electronic configuration. Okay, if you know the electronic configuration, you will see the answer there only. It is half filled, it is full filled, it has noble gas configuration. These are the points that you have to remember. These are the points that you have to observe while answering questions. Okay, so if you talk about Ti4+, it has noble gas configuration. Ti3+ has 1 electron in d orbital. Ti2+ will have 2 electrons in its d orbital. So they are saying Ti4+ is much more stable than Ti3+ and Ti2+. Yes, obviously, because in Ti4+ we have noble gas configuration. As simple as that. Okay, so this statement is true. Among the 3D series elements, only copper has positive reduction potential. You have seen this in your electrochemistry also. That copper has exceptionally high reduction potential. The SRP value of copper you should know. Okay, you have seen it so many times in your electrochemistry. Now we are repeating it here. It is 0.34 volt. Okay, so it is exceptionally high in comparison to all the other elements which are present in your 3D series. So that is correct. So this statement is true. What about the third statement? Both scandium and zinc, they exhibit +1 oxidation state. Now this statement is wrong. Okay, scandium will show +2 and +3 oxidation state. Zinc will show most commonly +2 oxidation state. But what is written in the statement? That scandium and zinc will show +1 oxidation state. That statement is wrong. Scandium will like to exist in +2 or +3 oxidation state, the common oxidation states which are shown by scandium, and your zinc will show +2 oxidation state. Okay, so the statement is false. So first and second is correct. They have asked you about the correct statement, so the answer will be option A. That is how you have to answer. Everything you can answer based on the electronic configuration of the elements that we were talking about. Okay, now let's move to the next question, everyone. Assertion: all copper halides are known except the iodide. That is true. See, Cu2+ has high reduction potential, right? Iodide also has high reduction potential. So if you compare, the one which has higher SRP will undergo reduction and the other element must undergo oxidation, right? This is what we have learned. But in case of copper, since so many copper ions are present in solution, copper iodide is also present in the solution. So instead of I-, you will find I2 in the solution. So CuI2 does not exist. That you expect. Copper itself will undergo reduction and it will oxidize your iodide to I2. Okay. So what will be present in the solution? Or CuI, not CuI2. Okay, so this statement, all copper second halides are known except the iodide, that is very much true. Okay, and the reason is that Cu2 plus oxidizes I minus to I2. This is also true. So both assertion and reason are correct, and reason is the correct explanation of assertion. You should know this as a fact. This is a very important observation. This has been as in your board examination also, you must have seen. There they will ask you the explanation. Here you just have to answer the question based on whether it is true or false. As simple as that. You don't have to explain it. Explanation is already given in the question. So that makes it very, very easy. Okay, see the next question. Which of the following are correct? Again, you have to identify the correct statement. So, vanadium 2 plus liberates hydrogen from a dilute acid. That is true. Okay. So, vanadium if they talk about vanadium 2 plus, this is vanadium 2 plus. Yes, it does liberate hydrogen from a dilute acid. This is your true statement. The earlier members of lanthanide series, they behave more like aluminium. This is wrong. The earlier members behave more like calcium, and your higher members, they are closer to aluminium. They will show properties similar to aluminium. Okay. So the earlier members of lanthanide series behave more like calcium, everyone. So this is false. The silver UK coins are made of copper nickel alloy. That is true statement. The maximum oxidation state exhibited by neptunium is +7. This is also true. So the question was which of the following statements are correct? Only statement 2 is incorrect. Rest of the statements are true. Okay, so your correct answer will be first, third and fourth. Option C. So you have to remember the effects, otherwise you will not be able to answer the question in D and F block elements. There are no numericals involved here. Okay, so read the NCERT thoroughly, revise it 2-3 times, and then you will be able to answer these questions very easily. Okay, see the next question. Chromium 2 plus and manganese 3 plus do possess D4 electronic configuration. So chromium 2 plus will readily like to convert into chromium 3 plus. Why? See the electronic configuration. If you remove 3 electrons, this is the electronic configuration for chromium. If you talk about chromium 3 plus, it will have 3D3 configuration, which is exceptionally stable. Okay, so if you have Cr2 plus ion, it will try to convert it into a more stable oxidation state, that is 3 plus. In order to do that, it will lose electrons, it will undergo oxidation. Okay, so chromium 2 plus will try to convert into chromium 3 plus. It is itself undergoing oxidation. So it will behave like a good reducing agent. Reducing agent reduces others, itself undergoes oxidation. Okay, so chromium 2 plus itself undergoes oxidation, will behave like a good reducing agent. What about Mn3 plus? For manganese, the 2 plus oxidation state is much more stable. So manganese undergoes reduction to form Mn2 plus. Why is Mn2 plus so stable? Because of half-filled d orbital configuration, 3d5. Half-filled and full-filled configuration has exceptional stability. Why? Because of high exchange value and low energy. Okay, so half-filled, full-filled, anywhere you see, blindly write it is much more stable than any other incompletely filled d orbital configuration. Okay, so Mn3 plus undergoes reduction to form Mn2 plus. It itself undergoes reduction, so it will behave like a good oxidizing agent. Reducing agent reduces others, itself undergoes oxidation. Oxidizing agent oxidizes others, itself undergoes reduction. Remember this, you have learned about it in redox reaction also. Okay, so which one is your true statement? Mn3 plus is a oxidizing agent, yes it is, while Cr2 plus is a reducing agent, option A. This is your true statement. Okay, so always look for stable electronic configuration, that will be the half-filled, full-filled or noble gas configuration. Okay, see the next question. Which of the following elements are not regarded as transition elements? Remember, in the beginning when we were talking about some important features of D block elements, I told you not every element that belongs to D block you can call as transition element. You have to see whether it has incompletely filled d orbital in its ground state or its common oxidation state. So follow that rule, and based on that you can say zinc, cadmium and mercury have completely filled d orbital. In the ground state, and their most common oxidation state. So that is why we call them as non-transition elements. Although they belong to D block, we don't call them as transition elements. These are non-transition elements. In order to call them as transition elements, they must have incompletely filled d orbitals in their ground state or their most common oxidation state. So your correct answer here is zinc, cadmium and mercury because of their fulfilled D10 electronic configuration. This one will have 3D10, 4D10, this one will have 5D10 electronic configuration based on the series you are talking about, 3D, 4D or 5D series. Okay, so this also is given in your NCERT direct questions. Okay, let's see the next question. Assertion: transition metals and their complexes, they show catalytic activity. Remember some important features about D and F block elements, transition elements, they show catalytic activity. So this statement is true. Okay. While to these transition metals show catalytic activity, the reason must be variable oxidation state. Okay, so see the reason now. The activation energy of the reaction is lowered by the catalyst. That is true. See, assertion is a true statement. Read them individually. First read assertion. If you read assertion, what can you say about it? Is it a true or false statement? So it is a true statement. Yes, transition elements, they show catalytic activity. Leave assertion now. Read the reason as a individual statement. Okay, don't try to relate it to assertion right now. Just read the statement and try to identify, is the statement correct or not? So the statement is correct that yes, if you are talking about a catalyst, if it is a positive catalyst, it will decrease the activation energy, it will change the mechanism of the reaction, and that is how it will increase the rate of reaction. Okay, but this reason is not the correct explanation of assertion. This is what we are concerned with. So your correct answer will be both assertion and reason are correct, but reason is not the correct explanation of assertion. It is not explaining why transition elements, they show catalytic activity. The reason should have been variable oxidation state. Okay. See the next one. Choose the correct statement. Fe3 plus ion is more stable than Fe2 plus ion. Whenever they ask you about the stability of oxidation state, what are you going to consider? The electronic configuration, as we have done so many different times in the previous questions. Remember that Mn3 plus question, that Cr3 plus question. What are we comparing? electronic configuration. Okay, so in this case also just compare the electronic configuration, you will get the answer directly. So why are we saying that Fe3 plus is more stable? See the electronic configuration. 3d5, Fe2 plus 3d6. Whenever we have half filled or completely filled d orbital configuration, it will show exceptional stability. So that is the reason why we can say Fe3 plus is much more stable than Fe2 plus. See the options now. More the charge on the atom, more is the stability. No, this is wrong. Configuration of Fe2 plus is 3d6, great, and while Fe3 plus is 3d5, half filled configuration, extra stability. Okay, so this reason is correct. Fe2 plus has a larger size than that of Fe3 plus. No, this is not the reason. And Fe3 plus ions are colored. This is also not the reason. Both of them will show color. Both of them have unpaired electrons. Okay. Now, let's see the next question. The valence shell electronic configuration for chromium and copper. See, chromium and copper, they don't follow the general electronic configuration of d block elements. Generally, what do? We add 2 electrons in the s orbital and rest of the electrons we add to d orbital. But in case of chromium and copper, we see something different. See, for chromium, the electronic configuration, you will think it should be 3d4, 4s2. Yes, you will definitely think this is the correct electronic configuration because that is how we have written for the rest of the elements. And your assumption is wrong. Based on experimental data, we come to know that since we have only 1 electron less than the half-filled d orbital configuration, instead of keeping the electron in s orbital, we will give it to d orbital. So this electronic configuration is wrong. It should be 3d5, 4s1. This is the exception that you have to remember. Similarly, for copper also, you will assume it should be 3d9, 4s2. Again, your assumption is wrong. We have only 1 electron less than the full-filled d orbital configuration. Again, we will take off 1 electron from the s orbital and we will add it to d orbital. So this is the correct answer. 3d5, 4s1, 3d10, 4s1. Option B is the correct answer. Okay. See the next question. The correct statement about chromium 2 plus and Mn3 plus among the following is. So we have done something similar just now, that chromium 2 plus is much more stable in 3 plus oxidation state. See, a similar question is repeated, but these statements, only the wording is different. They are asking you the same thing. You already know the answer. Just choose the correct statement according to the question. So again we will say chromium 2 plus will readily change into chromium 3 plus. Why? Because this is the stable oxidation state of chromium. It itself undergoes oxidation. It will behave like a reducing agent. What about Mn3 plus? Mn3 plus is less stable than Mn2 plus. Why? Because in this case you have 3d5 electronic configuration. Half-filled configuration is much more stable. So Mn3 plus will undergo reduction readily. It itself undergoes reduction. It will behave like a oxidizing agent. Itself undergoes reduction, is a oxidizing agent. Now see the statements which are mentioned here. Chromium 2 plus is a reducing agent. This is true. Mn3 plus is a reducing agent. No. Mn3 plus is a oxidizing agent as we have seen just now. Okay. See the third statement. Both chromium 2 plus and Mn3 plus exhibit D5 outer electronic configuration. This is also wrong. When chromium 2 plus is used as a reducing agent, it attains D5 configuration. No. It has 3D3 configuration. Okay. In this case, it has 3D4. So it will not attain 3D5 configuration. That statement is also wrong. Okay. So this is your correct answer. Chromium 2 plus is a reducing agent. In the question that we have done earlier, the statement that was correct, we have talked about both chromium 2 plus and Mn3 plus there. In this case, they have given the reason only for chromium 2 plus. No worries to us. We understand the reason. If they ask you about Mn3 plus in some new question, you can answer it easily. Okay. So you don't have to cram anything. If you know the electronic configuration, you know the answer to this question. Okay. See the next one. Which of the following characteristics of the transition metals is associated with their catalytic activity? Remember, we have done one question, assertion, reason question, in which we have said that transition elements, they show catalytic activity. That assertion was true. The reason was also true, but it was not explaining our assertion correctly. Now you know the answer to that question, because I have already told you, in order to understand the catalytic activity, you have to talk about variable oxidation state. So color of hydrated ions is the reason for the catalytic activity? No. Diamagnetic behavior is the reason? No. Paramagnetic behavior? No. I told you variable oxidation state. So in that question, if they would have written the reason to be that because transition elements show variable oxidation state, that is why we use them as the catalyst, then that question would have been correct. Okay. So the reason for variable oxidation, the reason for catalytic activity is variable oxidation state. Okay. Now, what is the correct order of oxidizing power of the given ions? Find out the oxidation state, you will know the answer. Okay. So what is the oxidation state of vanadium here? Use the X method. +3, right? So this is present in +3 oxidation state. Okay. What about chromium? +6. What about manganese? Okay. So based on that, what will be the correct order? As the oxidation number increases, the oxidizing power increases. So correct answer will be option A. As simple as that. What is the oxidizing power? The power to oxidize others. If you are oxidizing others, you will yourself undergo reduction. Okay. For manganese, +7 is the maximum oxidation state. It cannot show a higher oxidation state. So it will reduce to a lower oxidation state. This is how we understand the question. Higher the oxidation state, higher will be the oxidizing power. Okay. So correct answer here is option A. See the next question now. Identify the basic oxide from the following. Once again, follow the oxidation state. Okay. So what is the oxidation state of chromium here? +3. What about this one? +6. V2O5 +5. V2O3 +3. Okay. So they are talking about the basic oxide. As the oxidation number increases, the acidic nature of the oxide increases. So we have to look for lower oxidation state. But I have two such options in which I have +3 oxidation state. How to compare between them? As we move along the period, the basic nature decreases. Along the period, basicity of the oxide decreases. So a correct answer would be vanadium in +3 oxidation state. This is the most basic oxide out of everything that is mentioned here. Okay. In the last session, if you remember, we were comparing the oxidation state. We will do one such question in which you will talk about the acidic nature. There, just compare the oxidation state. Higher the oxidation state, higher will be the acidic character. As simple as that. Okay. See the next question. Cobalt third chloride, it forms a green colored complex X with ammonia. How many number of moles of silver chloride formed when excess of AgNO3 solution is added to this much ml of 1 molar solution? So, read the question in small steps. Read the first statement. What are they telling you? That there is some cobalt third chloride complex that is bonding with ammonia. Write that first. Okay, so this is the complex they are talking about. But we are not able to understand it in this way. Okay, this was given by Werner's theory. Let's write it in a way so that we can understand what is present inside the coordination sphere and what is present in the ionic sphere. Because the ions which are present outside the coordination sphere, they are present in solution. This is what we are trying to identify. Okay, so you can write it in this way. COCl3 NH3 whole thrice. Okay, sorry. So we can write it as CONH3 whole 4 Cl2, and there will be one chloride ion in the ionization sphere. Only the ions which are present in the ionization sphere will be present in the solution, because everything inside the coordination sphere does not dissociate further. That is the property of your coordination compound. That is how it differentiate between a double salt and your coordination compound or complex salt. Okay. NH3 whole 4 Cl2, only one chloride ion outside. Only this chloride ion will be lost in the solution. For that you are given the molarity and volume. So if you know the molarity and the volume, can you calculate the number of moles? Obviously you can. So one chloride ion per mole of this complex. So how many moles of chloride ions are present in the solution? Remember molarity, number of moles of solute over volume of solution in liters. So we are asked about the number of moles. So number of moles will be molarity into volume in liters. Molarity is 1 molar and volume is 100 over 1000 in liters, right? 0.1 moles. So if 1 mole of the complex gives you 1 mole of chloride ion, so 0.1 mole of the complex will give you 0.1 mole of chloride ion. Simple unitary mathematics. Okay. So your correct answer is option C. 0.1 moles are produced. Okay. See the next question. How many of the following ligands are stronger than water? See, direct question based on spectrochemical series that we have seen in the beginning. If you know the spectrochemical series, you can answer this question very easily. So what was the order we have covered? That in the beginning we will have halide donors, followed by oxygen donors, then nitrogen donors, and in the end carbon donors. Okay. So they are asking you which one is stronger than water. So only the nitrogen donors and carbon donors we have to count. Please see. Sulfite, weak field ligand. Bromide, weak field ligand. Oxalate, weak field ligand. Strong field ligand. Carbon donor. Ethylene diamine, nitrogen donor. Strong field ligand. Ammonia, again a nitrogen donor. Strong field ligand. Carbon donor, strong field ligand. Hydroxide, weak field ligand. So how many ligands are present here which are stronger than water? Only 4. Option C. So if you know the spectrochemical series, you know the answer directly. Please try to remember it. You will see many such questions here. Sometimes they will ask you the order also. In this case, they are just asking you how many are stronger. So you can decide accordingly. Okay, let's see the next question. Which of the following types of isomerism is exhibited by this particular complex? Okay, so the options are optical isomerism, linkage isomerism, ionization and coordination. See, in order to see optical isomerism, you should know about plane of symmetry and center of symmetry. If both plane of symmetry and center of symmetry are absent in your compound, then only we can call it as optically active compound. Now, what is plane of symmetry? It is some imaginary plane that will bisect your molecule into 2 equal halves. So, do we see a plane of symmetry in this complex? Yes, we have a plane of symmetry in this complex. So, will it show optical isomerism? No, it will not show any optical isomerism. Let me show you. So, optical isomerism is absent. Do we see this kind of plane of symmetry? Okay. Let me show it here with a different color. Okay. So, do we see this kind of plane of symmetry here, this one, in which your molecule is bisected into 2 equal halves? Okay. Try to imagine this. This is your imaginary plane which is bisecting your molecule into 2 equal halves such that the ammonia which is present above will show an exact image in the ammonia below. So, plane of symmetry is present. It is optically inactive. Plane of symmetry is present. So, that is why this molecule is optically inactive. What about linkage isomerism? Will it show linkage isomerism? It will definitely show linkage isomerism. Why? Because we have ambidentate ligand here. Okay. This is your ambidentate ligand. So, it can be present as ONO also. What is an ambidentate ligand? In which the same ligand can donate through 2 different donor atoms, but only one is able to donate at a time. So, it is not a bidentate ligand, it is a monodentate ligand only. Okay. What about ionization isomerism? It can show ionization isomerism also. The ions which are present outside the coordination sphere, they can rearrange themselves, go inside the coordination sphere and your ligands will come outside. So, yes, it will show ionization isomerism also. Okay. So, optical is not present, linkage is present, ionization is present, coordination isomerism is also absent. Why? In order to show coordination isomerism, I should have a positively charged and a negatively charged coordination sphere. I have only one coordination sphere here. Obviously, there will be no rearrangement of ligands between the 2 coordination spheres. So, coordination isomerism is also absent. Okay. So, your correct answer here will be second and third only. Option A. Okay. Let's see one last question, then we will end the session and rest of the questions you have to do as your homework. Okay. So, one last question. What is the coordination number? Such a simple question. What is the coordination number of the metal in this particular complex? I told you, in order to find the coordination number, you have to see the donor atoms. Please don't count the number of ligands and say the coordination number is 4 here. That would be a blunder. Ethylene diamine is a bidentate ligand. This is ethylene diamine, everyone. So it has 2 donor atoms which are linked to your central metal atom. Okay. So one such ethylene diamine ligand is bonded to your central atom through 2 donor atoms. I have 2 such ethylene diamine ligands, right? So how many donor atoms are there? 4. And in addition to that, I have chloride also, right? So coordination number here will be 6. You have to count the number of donor atoms. Please don't count the number of ligands. So correct answer is 6, not 4. Don't do that mistake. Okay. So please see what type of ligand is there, monodentate, bidentate, tridentate and so on, and accordingly answer. Okay. So that is all for today, everyone. We have learned about D and F block elements. We have learned about coordination compounds. We have solved questions based on spectrochemical series. Please try to revise the spectrochemical series. Please memorize it. You will see direct question based on the order, based on the strength, as we have covered today. Okay. So if you want to cover the rest of the EAPCET syllabus, you can download our sisyaclass app also. We have classes for mathematics as well for the EAPCET series. Those classes are 2 a day, and for chemistry, I will join you at 3:30 p.m. Try to use that information. Try to solve many more questions based on that topic we have covered today. We will give you the PDF of the questions also in the description. So try to see it. If you are facing any doubt, you can post it in the comment box. Okay. So that is all for today. Have a great day.